Hello, everybody. My name is Dolph Mathews, and this is Lance Bragstad. We're both engineers at Rackspace. I work in private cloud, and Lance works in public cloud. Both of our focuses is Keystone. So today we're going to be talking about Fernet tokens and how they can improve the response time and scalability of Keystone and ultimately OpenStack. So first of all, we're going to go through kind of a history and background of why on earth we need another token format, because you probably already know that we have UUID, PKI, and PKI-Z. Oops. And one of the most important attributes of Fernet tokens is that they're non-persistent. So we're going to go through why that matters. And then once we've convinced you that you need to switch all your deployments to use Fernet, we're going to explain how to do that, and then more importantly, how to scale that out in a clustered environment.
So getting into this a little bit more, we're going to kind of take a brief rundown of each token format available currently, and then compare that to Fernet and understand like the primary use case that each one kind of solves. So the first token format was a UUID token, 32 bytes long. They're super small and they're simple. The main use case that they were solving was that it was a way for services to authenticate and provide tenancy. They didn't require online validation as well as sort of like persistent backing.
So from like a historical perspective, the reason UUID was chosen as the technology of choice is that a bunch of Nova and Swift developers got together, and this is the simplest possible solution you can imagine. So issue secret and then validate it back end, and Nova and Swift guys are happy. So. That ultimately got replaced with, I would say, an experiment called PKI, which is a cryptographically signed document. This is actually base64 encoded-ish. It is a sort of proprietary encoding scheme, but you can actually B64 decode this if you fuss with it a little bit. And you'll see a CMS document. The CMS document contains the entire online validation response from Keystone that you get, including your service catalog, your identity, metadata about your identity, your tenancy, if you have one, just a whole boatload of information. Everything you would ever get back from Keystone is contained in that document. So this is an example of a very small PKI token, and it's a huge 1712 bytes. So just the size alone was a big problem with PKI tokens. They tend to break the internet, as I like to say. A lot of compiled software has like buffer sizes for things like headers, for example, in Apache HTTPD, and they all kind of default to around like 8,192 bytes. So as soon as you go beyond that, you start breaking things. So they also require a little bit of setup, which we consider to be a disadvantage, and revocation can be difficult because there's a lot of variables involved. They're designed to be validated offline, so you need a bunch of extra information so that you can securely validate them offline, including the certificates used to create it, so you can validate that. You need information about revocation events that occurred in Keystone. So for example, this tenancy has been disabled, otherwise, and you need to know that as a client to be able to validate that, and so on. So then we introduced PKI-Z, which is exactly like PKI, except we fixed some of the base64 encoding oddities that were in the first iteration, and we introduced Z-lib-based compression. So as you can plainly tell, this token is a lot smaller than the last one. I'll flip back and forth so you can see the gigantic difference. So like when your catalog has a bunch of redundancies in it, the compression actually does help quite a bit, but they're still gigantic. They still cause problems. They still break for people. So that brought us to Fernet.
And so Fernet, we needed a token format where we could solve non-persistent, but we still needed the ability to validate that token in multi-region deployments without having to wait for that replication time. So if we get rid of non-persistence, or if we make a token that's non-persistent, we still need to have that online validation aspect of it. So that's kind of where Fernet came in. And we keep it under 250 bytes for the same reason that we don't want to have the same issues where we get PKI. Which makes them just small enough. And by that, the token is built of an authorization context. So everything that you need to validate that token should live in that token. And so when you decrypt it, you should be able to pull up the information and use that as a way to validate the scope. So all that lives inside the token, you're eliminating the need for persistent context, which makes them not persistent. They do require additional setup. You do have keys that you need to encrypt and decrypt with, so that adds a little bit of setup to your deployment, and they also, at this point, require online validation.
So non-persistence is super important. If you've run a OpenStack deployment for longer than about a day, you'll know that you have a gigantic token table that you should be flushing if you're using like UUID tokens or PKI tokens. What happens is that Keystone writes all your tokens to a database and stores them there forever so that it can validate them until they ultimately expire. And then you can purge them, but that's an extra cron job you need to be running. And if you're just setting up OpenStack yourself, you're probably not running that cron job. So you run out of disk space on your database nodes. So with Fernet, this is what you'll see in a running environment. Token table is just empty, we don't use it. So like more broadly, non-persistence, token creation is like the most frequent operation that Keystone will see. So fewer backend writes means Keystone is faster. The fact that we can distribute the encryption and signing keys out to all your Keystone nodes means that when you create a token on one node, there's no like replication delay and Galera or whatever to make sure that in one region your tokens are already available in another region. Just have all your Keystone nodes sharing the exact same encryption and decryption keys, and there's no lag. You can create a token here and then halfway around the world use it immediately. So on that note, there's less to replicate. Your token table would be gigantic if you're using UUID, and you'd be replicating that halfway around the world if you have regions in, say, Australia and the US. And then we also ran a whole bunch of benchmarks and compared Fernet tokens, an early implementation of Fernet tokens back in like February to both UUID and PKI-Z. And you can see the numbers. It was substantially faster just because Keystone doesn't have to go to the database on validations, for example, ever. So, nothing you want to add?
So switching over to a Fernet implementation, it's a pretty easy change. You just got to change your provider to use a Fernet provider. And there are two optional configuration options. One's the location of your key repository on disk. And this is something that you can extend a little bit later on too if you want to use something else. And I'd be happy to talk to somebody about that afterwards, but we probably won't get into it here. The second one is max active keys, so the number of keys that you want to have active in your deployment before they start getting pruned. And then going into setup, pretty easy. Your Fernet setup is a one-time operation that you do, and then after that, you can do subsequent rotations, and that is kind of determined on your deployment security policy. So how often do you need to rotate your keys in order to be secure? And that's kind of a case-by-case thing, but that's something that you can do later on and just kind of rotate your keys and distribute them as you need to. So what we're going to do now is kind of go into like the rotation and the setup individually, and then show that in a couple of different cases, and then finish up with an example in like a multi-node environment to see how that benefits us. So the setup, it's really easy. If we give us like this situation where we have 4 max active keys and we run our setup once, it's going to initialize our key repository. So we'll end up with a staged key, and the staged key is always 0. The purpose of the staged key is that it's always going to be your next primary key, and by primary key, it's the key that actually encrypts and returns the token back. So your primary key is the one that's doing the encryption. And the second key, which is the primary, is always the one with the highest index. So after our initial setup, we'll end up with 2 keys, and when we go to rotate, we'll be promoting our staged key to be the new primary, and that essentially is a demotion, so we have to keep the secondary key around for some period of time because it was the primary for some period of time. So we have to have the ability to decrypt tokens that have been signed with that token. And so this pattern will kind of just repeat until we get to our max active key limit, in which case we will go through and add another step at the end and go through and prune old keys. So your max active keys is essentially the 4 latest keys that you've created. So this is that same thing, just represented differently, where you can kind of see the life cycle of each key as it goes through the rotation, and then as it gets pruned out. And that's what it would look like with 3. So the staged key in single node deployments doesn't really do a whole lot for you. Where you really get the benefit of a staged key is in a multi-node deployment. And so let's say we have max active 3 keys, and we want to distribute those across 3 Keystone nodes, and these could be multi-region, but we still want the ability to be able to validate a token that we get from node 1 immediately against node 3 without downtime. So our initial setup is going to occur on node 1, and then we'll have some sort of key distribution tool that goes through and replicates that key repository in different locations so that all of our Keystone nodes essentially have sync state.
So you'd have to be doing this outside of Keystone with your configuration management tool, whatever that is.
Sure. So now, at this point, everybody should be able to validate each other's tokens and not have any issues. And we should be able to do that immediately. Like, we shouldn't have to wait for any sort of replication to happen between validations. So we want to rotate. Some amount of time has happened, so we'll perform a rotation on node 1, introducing a new staged key, but we also have a new primary. So we have this period of time where if we go to validate, or if we go to authenticate against node 1, we're going to get a key back, or a token back that has been encrypted with key 2. We should still be able to do that validation because that staged key exists on nodes 2 and 3.
So the colors are actually representing the contents of the files. So key 2, 0, and 0. So this is the primary key being used to create tokens here. It can also be used to validate tokens over here because it's already been distributed. So if I go back, what actually happened was 0 became 2, we introduced a new 0, and then they all share each other's primary keys.
Yep. So then we go through and we make sure that all of our nodes sync state again, and we're essentially back to the beginning where we end up with a sync state across our deployment. So we go to rotate again. Now node 1, we've pruned our first key, but that shouldn't really matter because nodes 2 and 3 won't be signing anything with that key anyway. So at this point, we want to just clean up and continue to push our state. So that kind of shows the benefit of having a staged key and being able to solve that token validation problem in multi-region deployments.
No race conditions, yeah.
Yeah. So any questions, comments?
So you said this requires online validation. Would there be, is there some theoretically possible way to allow brief periods of offline validation? Like you get back some set of parameters so you can validate for 60 seconds if you're willing to forego, let your revocations be a minute stale?
Yeah, there's a few different ways that we kind of thought about going about this. We essentially ran out of time.
Okay.
It would be really cool to kind of have that built in. The thing about the Fernet spec was that it was upstream and someone already came up with it, so it was implemented in cryptography.
I don't know if it's a complete yes to your question though. We can do limited offline validation, which is like, is this actually a Fernet token? Is it expired? Things like that, because the timestamps are encoded sort of into plain text into the token itself. But you can't actually get any of the metadata out of it to really use it as a token. So you need to actually go back to Keystone at some point, unless you've already cached that validation in the past. So yes and no?
If I've done that, I may as well just cache the token.
Yeah, exactly. So.
You had performance improvements.
Mm-hmm.
Is that just for getting a token?
No, we did benchmarks on creating and validating tokens and a few other operations.
I asked just because, like, when
Sure.
you have Keystone problems and, like, maybe the token table is ginormous and it's bogging everything down, right?
Mm-hmm.
Makes everybody say the cloud is broken, whatever, throw things. I don't know how much faster it would make everything else, is, I guess, what I'm trying to get at. If you have, I know that's not something you can answer with, like, numbers or anything, but.
I mean, considering how many things call Keystone, I would say it will be noticeable.
Yeah, but I mean,
So.
you know, like you go to the Horizon page to show a bunch of instances, there's like 20 API calls that get made for that page.
Yeah, I will say for sure, as your token table bloats, for example, like it'll get slower and slower and slower. Fernet doesn't have that problem.
Right.
Doesn't matter how many tokens you've issued in the past 24 hours, each validation will take exactly the same amount of time. So,
I would say it makes everything faster.
yeah.
It's good. I mean, it's got to. It's just, I mean, I'm curious to see what it's going to do.
Go
Are
ahead.
the tokens cacheable? Are they reusable?
Yes. Yes. Yeah, they behave from an end user perspective, they behave exactly like UUID tokens. And so they also behave like UUID tokens from a middleware perspective.
And
So.
in Keystone, are they only enabled in V3, or is this something that can be enabled in V2?
This is V2 compatible as well.
Yeah.
So when we introduced the token format, it was determined that it should be in both.
So V2, V3, and introduced in Kilo. So
I'm sorry?
introduced in Kilo. Cool. Thanks,
Anyone
everybody.
else?